Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is capacitor partial charging and partial discharging. Our objective is to examine capacitors charged and discharged for time periods less than 5 time constants. Such short charge and discharge times result in end conditions other than the fully charged or fully discharged state. This lecture operates under the presumption the viewer is intimately familiar with both the capacitor charging process and the capacitor discharging process, as illustrated in the capacitor charging and the capacitor discharging lectures, both available at the Big Bad Tech channel. Additionally, it is presumed the viewer has watched the capacitor charging with initial conditions lecture, also available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. You'll recall we ended the capacitor charging lecture with a summary of the electrical properties of several example capacitor charging scenarios. To keep this lecture short and manageable, let's pick up where one of these examples left off. In case you don't have your notes, here's what we learned about example 1. Example 1 was a circuit consisting of a 12-volt DC source, a 15 microfarad capacitor, and 2 switches. Switch 1 serves to charge the capacitor through R1, a 200 ohm resistor, and switch 2 serves to discharge the capacitor through R2, a 400 ohm resistor. During the charging process, we learned at a time constant tau1 of 3 milliseconds. During the discharging process, we learned that at a time constant tau2 of 6 milliseconds. The capacitor is assumed to be initially discharged at t equals 0 as an initial voltage Vi of 0 volts. When switch 1 closed at time t equals 0, the transient charging process completed at 5 time constants, or 5 times 3 milliseconds, or 15 milliseconds. During the charge process, we observed the following behavior. Current through the capacitor, IC of t during the charging process was 60 milliamperes times e to the negative t over 3 milliseconds. Current through the capacitor experienced an initial surge of 60 milliamperes, which decayed to 0 by 15 milliseconds. Voltage across the capacitor, Vc of t during the charging process, was 12 volts times 1 minus e to the negative t over 3 milliseconds. Voltage across the initially uncharged capacitor started out at 0 volts and grew to 12 volts by 15 milliseconds. Current through resistor 1, IR1 of t during the charging process, also equaled 60 milliamperes times e to the negative t over 3 milliseconds. Current through resistor 1 and all elements in series with it experience an initial surge of 60 milliamperes, which decays to 0 by 15 milliseconds. Finally, voltage across resistor 1, VR1 of t during the charging process, was 12 volts times e to the negative t over 3 milliseconds. Voltage across resistor 1 surged to 12 volts and decayed to 0 by 15 milliseconds. Let's examine a partial charge scenario where switch 1 does not stay closed for the complete 15 milliseconds, but rather reopens at some intermediate time. Let's say switch 1 reopens at 6 milliseconds, 2 time constants into the charge process. Here's how you examine a partial charge scenario. Cut the graphs off at the time of interest, in this case t equals 6 milliseconds, and call it good. Where does a partial charge at 6 milliseconds leave us? This data is easily calculable. Substituting t equals 6 milliseconds into the expression for voltage across the capacitor, Vc of t, yields a final voltage of roughly 10.4 volts. We could substitute t equals 6 milliseconds into the other expressions to solve our other instantaneous values at the end of the partial charge. However, we can also use much simpler and more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Given the instantaneous voltage across the capacitor is 10.4 volts, an application of Kirchhoff's voltage law demonstrates that the voltage across resistor 1 must be 12 volts minus 10.4 volts, or the remaining 1.6 volts. A quick application of Ohm's law demonstrates that with 1.6 volts across R1, a 200 ohm resistor, approximately 8.1 milliamperes of current must be flowing through it, and by extension, 8.1 milliamperes must also be flowing into the capacitor because they are in series with one another. In summary, at t equals 6 milliseconds, Vc equals 10.4 volts, VR1 equals 1.6 volts, both IR1 and IC equal 8.1 milliamperes. The partial charge scenario ends here. In summary, any charge process lasting less than 5 full time constants results in a final charge state somewhere between the initial and final condition. If you know the initial conditions, the final conditions, and the time constant, solving for the intermediate state should be child's play by substituting the time of interest into the expression of interest. Too easy. Let's now examine a partial discharge scenario by picking up where we left off, notably at a condition in which the capacitor has not been charged up to the full 12 volts, but rather only 10.4 volts from the preceding partial charge phase. This represents the initial condition for the impending partial discharge scenario. Let's make our job easy by assuming the partial discharge scenario starts at some other t equals 0. We'll come back to correct this assumption in a moment when we examine a back-to-back partial charge and partial discharge scenario. Switch 2 serves to discharge the partially charged capacitor through R2 only. Tau 2, the time constant for the discharge path, is 6 milliseconds. If left to its own devices, this capacitor would fully discharge after 5 times 6 milliseconds or 30 milliseconds. For a partial discharge scenario, one would simply halt the discharge process at some intermediate state. Let's say switch 2 closes at this new t equals 0 milliseconds and remains closed only for 4 milliseconds. This is obviously smaller than the 6 millisecond time constant for the discharge path, and as a result, we'll most likely see this capacitor not fully discharged, but rather at some intermediate state of discharge. Let's derive the functions for the voltage across the capacitor, current through the capacitor, voltage across resistor 2, and the current through resistor 2 during the discharge phase. During the discharge phase, voltage across the capacitor, Vc of t, drops. It can be modeled as 10.4 volts times e to the negative t over 6 milliseconds. Voltage across the capacitor starts at 10.4 volts and drops. If we were patient enough to let it discharge for a full 30 milliseconds, we'd see it fully discharged at 0 volts. But we're just going to interrupt the discharge process at time t equals 4 milliseconds. Given there are only two elements in the discharge path, voltage across R2 must necessarily equal the voltage across the capacitor. VR2 will also equal 10.4 volts times e to the negative t over 6 milliseconds. During the discharge phase, current through the capacitor Ic of t experiences a momentary spike and then drops. When discharging, current leaves the capacitor. This reversal of current flow must necessarily be accounted for with the use of a negative sign. All current leaving the discharging capacitor must travel through the discharge path provided by R2. No prior convention has been established for R2, and as such, we're free to assume incoming current travels top to bottom. Ohm's law demonstrates that 10.4 volts applied across a 400 ohm resistor would result in an initial discharge current surge of 25.9 milliamperes. Current through the capacitor, Ic of t, can be modeled as negative 25.9 milliamperes times e to the negative t over 6 milliseconds, and IR2 equals 25.9 milliamperes times e to the negative t over 6 milliseconds. If we were given the luxury of switch 2 remaining closed for a full 5 time constants, in this case 30 milliseconds, we'd observe a fully discharged system. However, we're not going to wait that long. As we did with the partial charge scenario, simply cut the graphs off at the time of interest, in this case 4 milliseconds, and call it good. Let's see where we end up at t equals 4 milliseconds. Substituting 4 milliseconds into the expression for voltage across the capacitor, Vc of t, yields a voltage of roughly 5.3 volts. We could substitute 4 milliseconds into the other expressions. However, we can also use much simpler and more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Given the instantaneous voltage across the capacitor is 5.3 volts, this means the instantaneous voltage across resistor 2 must also be 5.3 volts. A quick application of Ohm's law demonstrates that with 5.3 volts across R2, a 400 ohm resistor, approximately 13.3 milliamperes of current must be flowing through it, and by extension, 13.3 milliamperes must also be flowing out of the capacitor because they are in series with one another. In summary, at t equals 4 milliseconds, the partial discharge phase ends with Vc equal to 5.3 volts, VR2 also equal to 5.3 volts, and both IR2 and Ic equaling 13.3 milliamperes, only one is incoming and the other outgoing. Note if both switch 1 and switch 2 remained open beyond this partial discharge, assuming an ideal capacitor with no internal leakage, we'd see this capacitor indefinitely maintain a 5.3 volt partial charge. Let's now examine a back-to-back partial charge and partial discharge scenario by overlaying our previous analyses on top of one another. All we really need to do is stitch our previous analyses together on one single timeline. Consider a scenario in which the capacitor is initially uncharged at 0 volts, and switch 1 closes at t equals 0 and reopens at t equals 6 milliseconds, 2 time constants into a charge phase. During the partial charge, we'd see voltage across the capacitor rise from 0 volts to 10.4 volts over a span of 6 milliseconds. Current through the capacitor would spike at 6 milliamperes, and 6 milliseconds later, it would have decayed to 8.1 milliamperes. The partial charge ends at t equals 6 milliseconds and the partial discharge phase begins. Switch 1 opens and switch 2 closes. The larger circuit's t equals 6 milliseconds is kind of like the partial discharge phase's t equals 0 milliseconds. If you want to, you can add accessory vertical axes to remind you of the switchover. All you really have to do is reference any previous time values from this new start point. For this partial discharge scenario, switch 2 reopens 4 milliseconds later at the larger circuit's t equals 10 milliseconds. During the partial discharge, voltage across the capacitor drops from 10.4 volts to 5.3 volts over a span of 4 milliseconds. Current through the discharge circuit spikes at 25.9 milliamperes, and 4 milliseconds later it decays to 13.3 milliamperes. The partial discharge ends when switch 2 opens at t equals 10 milliseconds, with a steady state 5.3 volts appearing across the partially charged and partially discharged capacitor. A suitable analogy for this back-to-back process might be as follows. Fill up a 12-gallon jug with only 10.4 gallons of water. Then empty it until only 5.3 gallons remain. Don't make partial charge and partial discharge analysis hard. Perform an analysis as if it was a full charge or a full discharge and simply cut the process off at the time of interest. In the case of a back-to-back partial charge and partial discharge scenario, one stage's end state is the other stage's starting point. Related to this observation, if we conducted another 6 millisecond partial charge from this initial condition, we might see the capacitor attain a higher final voltage at the end of the partial charge, given the 5.3 volt head start. Skipping the tedious math, another 6 millisecond partial charge would result in the capacitor achieving a voltage of approximately 11.1 volts. If we began another 4 millisecond partial discharge from this new higher state of charge, we might see the capacitor obtain a higher final voltage at the end of the partial discharge. Again, skipping the tedious math, another 4 millisecond partial discharge would result in the capacitor achieving a final voltage of approximately 5.7 volts. The observant among you will note that the second cycle resulted in slightly higher voltage values than the first. This being said, I'll caution you against making any premature conclusions about this upward creep. The next couple cycles will result in eventual stabilization of this system. Note how the end of the second partial discharge was higher than the end state of the first partial discharge. However, it wasn't nearly the dramatic leap we observed between the initial condition and the end state of the first partial discharge. I'll not bother you with wearisome calculations for the next couple back-to-back cycles because the change is so inconsequential, but here's what you might observe. Assuming we repeatedly partially charge this system for 6 milliseconds, immediately followed by a 4 millisecond partial discharge, we might see voltage across the capacitor continue to oscillate between 11.2 volts and 5.7 volts. If you want to go out 3 decimal places, you're looking at an upper limit of approximately 11.151 volts and a lower limit of approximately 5.725 volts. Like I said, the change for the next couple cycles is so inconsequential, the calculations are almost pointless. Once conditions stabilize, ultimately these repeated partial charges and partial discharges yield a quasi-wave-like DC voltage across the capacitor that bounces between approximately 11.2 volts and 5.7 volts. Despite the peaks and valleys, what we've obtained is in effect some steady-state average DC value between 11.2 volts and 5.7 volts, i.e. something different than the constant 12 volts capable of being supplied by this source. This is pretty cool, and it's a feature employed in a number of power electronics devices to change one level of DC to some other desired value. We'll examine buck choppers, a type of DC to DC converter that uses a related methodology to reduce DC output from a fixed source in later lectures. The point of this extended example is to demonstrate that partially charging and partially discharging a capacitor isn't necessarily that difficult to conceptualize. In summary, derive the functions for the properties of interest as if it were to be a full 5-time constant charge or discharge, and then just cut the graphs off at the intermediate time of interest. Instantaneous values at the time of the switchover can be easily obtained by substituting in the time of interest. If you're presented with a back-to-back partial charge and a partial discharge or vice versa, the end state of one process is the beginning of the other. Let's move on to another illustrated example of a back-to-back partial charge and partial discharge scenario. By now, you've had ample experience with charging, discharging, charging with initial conditions, and now partial charging and partial discharging scenarios. Let's put all these skills to the test at once with one giant exercise. If you stumble across the finish line with your sense of dignity still intact, you're tracking, and you could probably move on to the next lecture in the series. If not, you may wish to revisit and review those procedures that gave you trouble before you continue on. Let's make use of a totally new circuit consisting of a 16-volt DC source, 2 switches, and a 20 microfarad capacitor. Switch 1 serves to charge the capacitor through R1, a 200 ohm resistor, and switch 2 serves to discharge the capacitor through R2, a 100 ohm resistor. Let's assume this capacitor begins the analysis with an initial voltage of 2.1 volts, oriented positive to negative top to bottom. Let's make this a 2-part exercise. The first part being a partial charge scenario, in which switch 1 is closed and switch 2 is open from t equals 0 to t equals 1 millisecond. In ordinary circumstances, we'd expect this capacitor to eventually charge up to 16 volts, but as we'll learn, 1 millisecond is much too quick to allow a full charge. For stage 1, see if you can solve for the time constant tau1 associated with this partial charge process. Next, determine the instantaneous initial values for the voltage across the capacitor, the current through the capacitor, the voltage across R1, the current through R1, the voltage across R2, and the current through R2 at time t equals 0. Then, see if you can determine the time-varying expressions for the voltage across the capacitor, the current through the capacitor, the voltage across R1, the current through R1, the voltage across R2, and the current through R2 between t equals 0 and t equals 1 millisecond. Finally, see if you can determine the instantaneous values for the voltage across the capacitor, the current through the capacitor, the voltage across R1, the current through R1, the voltage across R2, and the current through R2 at time t equals 1 millisecond when the partial charge process ends. Once we've examined the partial charge process, we'll take a look at the partial discharge. By all means, pause the lecture and try stage 1 on your own. If you're tracking, you should obtain the following data. At t equals 0, switch 1 closes and switch 2 opens. The capacitor will charge through R1 only. R2 experiences no current and no voltage drop from t equals 0 to t equals 1 millisecond. Substituting our given values for R1 and the capacitor, we find tau1 to be 4 milliseconds. We should expect a full charge to be obtained after 5 time constants, or 5 times 4 milliseconds, or 20 milliseconds. Given this partial charge only lasts for 1 millisecond, or 1/4 of tau1, or 1/20th of a full charge, we should expect the capacitor to obtain only a small fraction of the potential 16-volt charge available. At t equals 0, the initial voltage across the capacitor is 2.1 volts. Kirchhoff's voltage law demonstrates that R1 experiences a differential of 16 volts minus 2.1 volts, or 13.9 volts at t equals 0. The application of Ohm's law demonstrates that R1 and the capacitor will experience an initial surge of 69.5 milliamperes at time t equals 0. Given these initial values and time constant, one can determine the time-varying expressions for the properties of interest during the partial charge process between t equals 0 and 1 millisecond. Voltage across the capacitor as a function of time, Vc of t, can be expressed as Vf plus Vi minus Vf times e to the negative t over tau, where Vi is the initial voltage of 2.1 volts, Vf is the final steady-state value of 16 volts, and tau is the time constant 4 milliseconds. Substituting in these given values, Vc of t resolves itself to its most simplified form as 16 volts minus 13.9 volts times e to the negative t over 4 milliseconds. If given a charge of sufficient length, in this case 20 milliseconds, we'd expect this capacitor to eventually reach 16 volts. However, we're going to interrupt the charge process very early, and as such, we might expect a much smaller final voltage. Voltage across R1 as a function of time, Vr1 of t, can be expressed as 13.9 volts times e to the negative t over 4 milliseconds. Current through the capacitor, Ic of t, can be expressed as 69.5 milliamperes times e to the negative t over 4 milliseconds, as can Ir1 of t. The partial charge ends when switch 1 opens at t equals 1 millisecond. Substituting 1 millisecond into the time-varying expressions for voltage across the capacitor demonstrates the capacitor achieves a charge of approximately 5.2 volts. As we anticipated, such a short charge process resulted in a partially charged state. Given 5.2 volts across the capacitor, Kirchhoff's voltage law demonstrates that at the time of switch 1's opening at t equals 1 millisecond, R1 must be experiencing a 16 volt minus 5.2 volt, or approximately 10.8 volt drop. An application of Ohm's law demonstrates that at the time of switch 1's opening at t equals 1 millisecond, R1 and the capacitor must be experiencing 54.1 milliamperes of current. You know, at the time of switchover, current is still flowing through R1 because the capacitor is still charging. Let's now move on to stage 2. Stage 2 is a partial discharge scenario, in which switch 1 is open and switch 2 is closed from t equals 1 to 2 milliseconds. In ordinary circumstances, we'd expect this capacitor to eventually fully discharge to 0 volts, but as we'll learn, 1 millisecond is much too quick to allow a full discharge. For stage 2, see if you can solve for the time constant tau2 associated with the partial discharge process. Next, determine the instantaneous initial values for the voltage across the capacitor, the current through the capacitor, the voltage across R1, the current through R1, the voltage across R2, and the current through R2 at t equals 1 millisecond. Then see if you can determine the time-varying expressions for the voltage across the capacitor, the current through the capacitor, the voltage across R1, the current through R1, the the voltage across R2, and the current through R2 between t equals 1 and 2 milliseconds. To make your job easy, my advice would be to simply assume the partial discharge starts at another t equals 0. This method sure beats including a 1 millisecond offset into each and every equation. Finally, see if you can determine the instantaneous values for the voltage across the capacitor, the current through the capacitor, the voltage across R1, the current through R1, the voltage across R2, and the current through R2 1 millisecond into the partial discharge process when switch 2 opens and the partial discharge process ends. Once we've examined the partial discharge process, we'll then plot these values as a function of time. By all means, pause the lecture and try stage 2 on your own. If you're tracking, you should have obtained the following data. Substituting in our given values for R2 in the capacitor, we find tau 2 to be 2 milliseconds. We should expect a full discharge to be obtained after 5 time constants, or 5 times 2 milliseconds, or 10 milliseconds. Given this partial discharge only lasts for 1 millisecond, or half of time constant tau 2, or 1/10 of a full discharge, we should expect the capacitor to only partially discharge. The initial voltage across the capacitor at the onset of the partial discharge is that value obtained during the previous partial charge, in this case 5.2 volts. Given there are only 2 elements in this discharge circuit, R2 also experiences a differential of 5.2 volts at t equals 1 millisecond. An application of Ohm's law demonstrates that R2 will experience an initial surge of approximately 51.7 milliamperes at t equals 1 millisecond. The capacitor must therefore be supplying 51.7 milliamperes at t equals 1 millisecond. To account for this reversal of current flow, the instantaneous value of current through the capacitor is to be considered negative. Given these initial values and the time constant, one can determine the time-variant expressions for the properties of interest during the partial discharge process. Again, assume the partial discharge process begins at another t equals 0. This method sure beats trying to include a 1 millisecond offset for each and every equation. Voltage across the capacitor as a function of time, Vc of t, can be expressed as 5.2 volts times e to the negative t over 2 milliseconds. If given a discharge of sufficient length, in this case 10 milliseconds, we'd expect the capacitor to eventually fully discharge to 0 volts. However, we're going to interrupt the discharge process very early, and as such, we might expect it to still carry a residual amount of voltage. Voltage across R2 is a function of time. The R2 of t can also be expressed as 5.2 volts times e to the negative t over 2 milliseconds. Current through the capacitor, IC of t, can be expressed as negative 51.7 milliamperes times e to the negative t over 2 milliseconds, where the 51.7 milliamperes is the magnitude of initial discharge current surge, and the negative sign indicates current is leaving the discharging capacitor. Current through R2, IR2 of t, can be expressed as 51.7 milliamperes times e to the negative t over 2 milliseconds, where the positive sign indicates current is entering R2. The partial charge ends at t equals 2 milliseconds when switch 2 opens. The time 2 milliseconds for the larger circuit represents a time of 1 millisecond in the discharge process. Substituting 1 millisecond of the time-varying expression for voltage across the capacitor during the discharge phase demonstrates the capacitor will be discharged to approximately 3.1 volts. Given there are only 2 elements in this discharge circuit, R2 will also experience a differential of 3.1 volts, 1 millisecond into the discharge process at the larger circuits t equals 2 milliseconds. An application of Ohm's law demonstrates that at the time a switch 2 is opening at 2 milliseconds, R2 and the capacitor must be experiencing 31.4 milliamperes of current, only one is incoming and the other outgoing. You'll note when switch 2 opens at t equals 2 milliseconds, current is still flowing through R2 because the capacitor is still discharging. There you have it, a complete analysis of a partial charge with an initial condition, followed by a complete analysis of a partial discharge. Note each partial process was characterized by a time span smaller than 5 time constants, and as such each partial process ends at some intermediate state other than a full charge or a full discharge. All the hard work is done, and the only task that remains is to plot these values. Stage 3, get out your crayons and draw a plot of voltage across the capacitor, a plot of current through the capacitor, a plot of voltage across R1, a plot of current through R1, a plot of voltage across R2, and a plot of current through R2 from t equals 0 to 2 milliseconds. Note 1 millisecond will serve as the transition from the partial charge to the partial discharge, and if you want to, you can draw an accessory vertical axis to remind you of the switchover. By all means, pause the lecture and try stage 3 on your own. If you're tracking, your plots should look something like this. Voltage across the capacitor looks like this. At t equals 0, it initiates the partial charge at 2.1 volts and climbs up to 5.2 volts by 1 millisecond. During the partial discharge, voltage across the capacitor drops from the previously obtained 5.2 volts down to 3.1 volts 1 millisecond later at 2 milliseconds. Note that voltage across the capacitor never underwent an instantaneous transition or sudden reversal in polarity, but rather did a nice, smooth, predictable ramp up and down. Current through the capacitor looks something like this. During the partial charge at t equals 0, it experiences an initial surge of 69.5 milliamperes of incoming charge current. By 1 millisecond, incoming charge current has decayed to 54.1 milliamperes. During the partial discharge, current through the capacitor does an instantaneous reversal and experiences an initial surge of 51.7 milliamperes of outgoing discharge current. 1 millisecond later, at 2 milliseconds, outgoing discharge current has decayed to 31.4 milliamperes. Again, note that the negative sign indicates reversal. During the partial charge, current came in. During the partial discharge, current went out. Voltage across R1 looks something like this. During the partial charge, it experiences an initial spike of 13.9 volts and then decays to 10.8 volts by 1 millisecond. Given switch 1 remains open during the partial discharge, R1 experiences no voltage drop from t equals 1 to 2 milliseconds. Current through R1 looks something like this. During the partial charge, it experiences an initial spike of 69.5 milliamperes, which decays to 54.1 milliamperes by t equals 1 milliseconds. Note at the time of the switchover at t equals 1 milliseconds, R1 is experiencing voltage and current because the capacitor charge process is being interrupted. Given switch 1 remains open during the partial discharge, R1 experiences no current through it from t equals 1 to 2 milliseconds. Voltage across R2 looks something like this. Given switch 2 remains open during the partial charge, R2 experiences no voltage drop from t equals 0 to 1 milliseconds. During the partial discharge, it experiences an initial spike of 5.2 volts, which decays to 3.1 volts 1 millisecond later at t equals 2 milliseconds. Current through R2 looks something like this. Given switch 2 remains open during the partial charge, R2 experiences no current through it from t equals 0 to 1 millisecond. During the partial discharge, it experiences an initial spike of 51.7 milliamperes, which decays to 31.4 milliamperes 1 millisecond later at t equals 2 milliseconds. Note when switch 2 opens at t equals 2 milliseconds, R2 is experiencing voltage and current because the capacitor discharge process is being interrupted. As we've noticed in previous lectures, several important takeaways should be immediately identifiable during this back-to-back partial charge and partial discharge scenario. During the partial charging process, current rushes through R1 and into the capacitor. While charging, voltage across the capacitor rises. In this example, we've included an initial voltage of 2.1 volts. A short partial charge results in some intermediate charge state, in this case 5.2 volts. During the partial discharge process, current rushes out of the capacitor through R2. While discharging, voltage across the capacitor drops. The short partial discharge results in some intermediate discharge state, in this case 3.1 volts. Any voltage drop experienced by resistors R1 and R2 are simply a consequence of the incoming and outgoing current experienced by the capacitor during the partial charge or partial discharge process. Importantly, voltage across the capacitor, whether charging or discharging, never undergoes a disjointed instantaneous transition or sudden reversal in polarity. That's the point. Capacitors resist sudden changes in voltage and are often employed in circuits that necessitate relatively steady or slowly changing voltage conditions. Also, it's kind of hard to notice on these plots given their scale. However, there is some asymmetry between the charge and discharge process. This is the consequence of R1 being a 200 ohm resistor, and R2 having a resistance value of half that at 100 ohms. Note the capacitor is partially charged for 1 milliseconds, which represents 1/4 of time constant tau 1, or 1/20th of a full charge, whereas a partial discharge of the same 1 milliseconds represents half of time constant tau 2, or 1/10th of a full discharge. You'd have to zoom in real close to notice any change in slope, but it does exist. As in our previous example, if we repeatedly partially charged and partially discharged this capacitor on a regular 1 millisecond basis, we might notice a slow rise and eventual stabilization of the system. Again, I'll not bother you with the tedious calculations for the next couple back-to-back cycles because the change is so inconsequential, and I know you're just dying to go play hacky sack in the parking lot with your fellow nerds, but here's what you might observe. Assuming we repeatedly partially charge this system through R1 for 1 millisecond, immediately followed by a 1 millisecond partial discharge through R2, we might see voltage across the capacitor continually oscillate between 6.7 volts and 4.1 volts. If you want to go out 3 decimal places, you're looking at an upper limit of approximately 6.708 volts and a lower limit of approximately 4.068 volts. And this is after like 7 or 8 cycles. If you got a lot of time on your hands, you are welcome to do these calculations yourself, but I do not recommend it. All right, I do believe I've hammered you enough for today. We'll examine more sophisticated capacitor charging and discharging scenarios in later lectures. In conclusion, we examined capacitor partial charge and partial discharge scenarios. We learned any charge or discharge process lasting less than the full 5 time constants results in the capacitor achieving some intermediate stage of charge or discharge. Additionally, we learned to calculate specific electrical properties at specific times and plot the results of our calculations on a graph. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.